Hi, everybody. Welcome to Chapter 14. And Chapter 14 is all about heat. Actually, we are doing chapters 13, 14, and 15 in your textbook. There are actually 3 chapters. I call it 14 because that's easier on my crazy little brain. In your textbook, we're doing all of 14, parts of 13, and parts of 15. Heat is a big topic. We're going to be on it for 2 full weeks. We're covering everything from thermal expansion, the fact that when you take a pickle jar and you can't get the lid off, you put it under hot water, and it's because the metal lid expands when it gets warm. And that expansion, that thermal expansion, explains everything from why roadbeds buckle when it's 95 degrees out in the summertime, to why there are expansion joints in bridges and things like that. We're going to talk about the difference between heat and temperature. They're not the same thing. Heat flows between objects, and temperature is really the measurement of internal kinetic energy of particles. We're going to talk about calorimetry. How do you measure how much heat one object can give another? The classic example is if you touch something like a piece of paper with your hand, that piece of paper may not feel terribly warm under your skin, but if you touch something else like a tabletop, it might feel cooler than that piece of paper. But they're sitting on the same desk and they're sitting next to each other. Why are 2 things in the same room at the same time feel different temperatures? That's because they are both different at giving heat to the environment, and that has to do with their specific heat. We're going to talk about methods of heat transfer: conduction, convection, radiation, and a little bit about the laws of thermodynamics. We're not going to get into the big mathematical laws of thermodynamics, but we're going to talk about them because they are as important as Newton's laws for dynamics and forces transferring. The laws of thermodynamics are the big rules of how heat transfers from place to place. So this is a big 2-week chapter. We have 2 labs, and in this video we're going to talk about the first lab, and then I'll come up with another video to talk about that second lab. So let's take a look at Canvas and what we've got going. So thermal expansion, as always, a study guide, a bigger collection of homework problems because this is a big 2-week chapter. As always, please don't try and do them all at once. Please do them by topic. Heat versus temperature, outline of those laws of thermodynamics, and by the time you have gotten through this portion, you're ready for that first lab. Now, since this is a big 2-week chapter, I would request that you get this far in the first week. If you do that, then, my friends, this far through the lab during the first week, if you do that, then you will be on track time-wise. You will not be behind. And sometimes timing is, when you're working at home, is the hard part. So if you've watched all these videos, done homework problems through calorimetry, you're going to be in good shape. Then the second week, we're going to start talking about latent heat, methods of heat transfer, do that second lab, and we're going to have a big test over heat and that small chapter we did last time on pressure. And remember, pressure was kind of a smaller idea, less homework problems, and that's going to be at the end of this chapter. So let's take a look at that specific heat lab. We have 2 versions. We have the one that's in your packet, and we have the more updated one for the do-at-home version. This is the one that you have in your packet. Now, I've designed the do-at-home one so that you can use the same data table, and what you are basically turning in are the calculations. And then I have added, instead of an explanation of error, I have added to show me the percent error, percent difference calculation, and then a different question. So when it comes to point distribution, the points are going to be distributed differently. It's not distributed as they are here. Why? Because I'm taking all the data for you. So there's not points given for how you collect your data. That just wouldn't make sense. But the calculations, you can do those on a separate piece of paper. Scan those in, take photos, however you're uploading your homework, and attach those with your data table, and that will be just fine. If you want a more organized version, here's the specific at-home version of the lab. So in calorimetry, calorie is how you measure heat. And we're going to use as our fancy calorimetry cup, 2 styrofoam cups. Now, if we were doing this in our laboratory at the college, we would actually be using a different calorimeter. I'm simplifying this experiment, and to simplify the experiment, I am using 2 styrofoam cups. Why? It makes the math a little easier, and since I'm not there to help you, I wanted to make this as simple as possible. So all of our reactions are going to occur in this calorimeter cup, and it has a little lid that will go on top. And the idea is styrofoam is a really great insulator. Very little heat will be lost. The big idea through all of this, the big idea is conservation of energy. The heat lost by one object is going to be equal to the heat gained by another. So whose or what is going to lose heat? Well, we're going to have hot metal that's going to lose heat, and it's going to be gained by cold water. And for each half of that equation, we're going to use this basic equation. Quantity of heat is mc, C stands for specific heat, and delta T is change in temp. So there is going to be the mass of the empty calorimeter cup, the mass of the piece of metal while it's dry. Then the calorimeter cup, a little bit of water gets added, and here is the mass of the cup plus a little bit of water and its beginning temperature. So this information can be used to calculate the quantity of heat before the reaction occurs. And then the piece of metal is heated. How did I heat the metal? And I did this on my kitchen stove at home. I put it in a boiling pot of water on my kitchen stove. I allowed it to be in there at least 2 minutes to reach equilibrium temperature with that boiling water. I took the temperature of the water right before I took it out. I brought home a digital thermometer from the lab, took the temperature of the boiling water, and then very quickly I put this hot piece of metal into the cup plus the water. I let the two equalize for a couple minutes, and then I took the final temperature of the mixture. And the final temperature of the mixture of the piece of hot copper plus the cup and water, the equilibrium temperature for copper was 18.9. Now, here's what you're going to do. You're going to do the math, and you are going to calculate the final temperature of the copper mixture. Now, I just took the final temperature as 18.9. You are going to mathematically solve for final temperature. There were multiple example problems that we did doing this. So use the data that I have photographs to show you. This is the primary equation. Remember, you're solving for final temp. Remember to set up the equation so that delta T's are positive. You may not know what I mean right now, but after you've gone through the videos, that'll make sense. Remember, heat lost by the metal is going to be equal to the heat gained by the cold water. You don't need to include the styrofoam cup in the calculations because it absorbs almost zero heat. And you are going to have to look up specific heats for water and for the metal we're talking about. Where can you look those up? Well, you can look them up on the pink sheet that I gave you early in the semester or on the internet. Please be sure that you are being consistent with your units. Grams, kilograms, joules, calories. You must have consistent units throughout your calculation. And you're going to show me that calculation. You're going to show me a percent error, and then you're going to repeat all this for tin and for lead. And then a final question about, I was very, very careful when I did this to not transfer an awful lot of hot water with the metal into the cup. And why is that important? Now, ladies and gents, quite bluntly, when I did this experiment at home, I did a real big happy dance because I got great results. So when you do percent errors, you're going to get great results if you do the math right. So if you get 40% error, you didn't do the math right, because all three of the metals ended up producing low percent errors, well below 10% error. And that's going to be a good indicator that you have done your mathematics correctly. So as always, I miss you. Sorry that we're not doing this in person. As you have questions, please holler. And hopefully, I'll be able to see you in person someday soon. All right. Have a good one. Bye-bye.